everybody, welcome back to Measure Theoretic Probability. In today's video, we're finally going to talk about random variables. Now, I'm sure you've seen random variables before, but what level have you seen them at? You might have seen them at a very sort of what I would call beginner level, where a random variable is a variable that takes on different values with different probabilities. For example, I'm going to define a random variable x to take on the value 1 with probability 1/4, 2 with probability 1/3, and 3 with probability 5/12. We are going to stick with the convention in all of probability and statistics that all random variables are denoted with capital letters. And yes, that is my capital X. My lowercase x is a little curlier and definitely smaller. Now, there's maybe an intermediate definition for a random variable that you might have seen, and this is where you start thinking of it as a function, taking outcomes from an experiment involving probability and assigning numbers. For example, suppose that we flip a coin one time. We've got a sample space that you might call omega. Remember, we're before measure theoretic probability here, so we don't have a probability space, but a set of possible outcomes, a sample space omega, consisting of heads and tails, and we might define a random variable capital X to be 1 if we get heads on the coin, and 0 if we get tails on the coin. So this is a function of the elements in omega, which gives us some real numbers, not very many real numbers, but some of them. And you may not have written it like this, but you can write it so it looks like a function that takes the value h and gives you the value 1, or takes the value t and gives you the value 0. So this is what I would call an intermediate definition, even if you never wrote it like this, thinking of it as a function from an experiment and assigning numbers to events. But we are in measure theory, so we are ready for the pro definition. We're going to start with a probability space consisting of a non-empty set omega, a sigma field curly f, and a probability measure p. A random variable x is going to be a function from omega to r that is measurable. This is what we need to define today. So remember that when we first talked about sigma fields, we were trying to collect sets on which we have defined measures, like a generic measure mu or a probability measure p. And then we maybe have defined measures for certain sets in F, and then we get others for free, like using the countable additivity property to get the probability measure for a union of disjoint sets, as just an example. So the sets in F are our measurable sets. These are events for which we know probabilities. And I will define this more formally, but for now, I just want to say that the function x is measurable with respect to this space if any probability you want to compute for x, if that probability can be gotten by you looking at the appropriate set in the sigma field F. So I have examples coming up in just a moment, but we say, and I have a more formal definition of measurability, but this is what we mean when we say that x is a measurable function, and it is, as you see, with respect to a sigma field. So we might say measurable with respect to f, or f measurable, or even measurable f. As an example, suppose that someone is flipping a coin 3 times, and suppose that you and I know nothing about coins or how coins work in terms of probabilities. But that person who's flipping the coin gave us some information about some probabilities. They defined a set A to be these outcomes here, which are all the outcomes that have at least 2 heads. And they gave us the probability measure of this set. And suppose, while we don't know about coins, we do know a little bit about probability measures, and we know that the probability measure of a complement should be 1 minus the number they gave us. And we know the empty set and the omega, those measure to 0 or 1 respectively. So consider the sigma field consisting of the 3 sets, the empty set, A complement, and omega. This is a sigma field. It's the sigma field generated by the set A, and currently they are all the sets that we know how to measure. So given that we know how to measure certain sets, a function x from omega to r is measurable with respect to this sigma field if all probabilities for x are now defined. So I want to get a little more specific. What kinds of things could we compute? I guess I need a random variable first. So I'm going to define a random variable capital X to be 1 if the 3 coin flip outcome resulted in at least 2 heads, and 0 otherwise. Now, the probability that x equals 1, we will assign the value 1 if we see at least 2 heads, and that is the event A, and we do know the probability that A occurs. So the probability that x equals 1 is the probability measure of the set A, and that has been defined. So we can compute at least that probability for x. Now, the probability that x equals 0 means that we did not see at least 2 heads. We saw 1 or fewer, and that is the probability measure of A complement, which has also already been defined for us. So basically, we have enough information for this random variable using probabilities on the measurable sets in curly F. Again, we say that this x is measurable with respect to F, sometimes just measurable if it's clear, and therefore, because it's a function from omega to r and measurable with respect to x, it is a valid random variable on this probability space. What if we stay with the same space, the same coin tossing example, and the A and A complement, and define a new random variable x to be the number of heads in the 3 coin flips? So x can take on the value 0, 1, 2, or 3, and we have a problem now, given the information at hand. The probability, for example, that x equals 1, this means we see exactly 1 heads in the 3 coin flips. So this corresponds to us having to measure the set consisting of the 3 outcomes: heads, tails, 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 heads, tails, or tails, tails, heads. But we don't know the probability measure of this set. It wasn't given to us. So sticking with the same probability space, defining the random variable a little bit differently, this is not a random variable with respect to this probability space. It is not a measurable function. So that's the idea behind measurable functions, but I do need to state this a little more formally. So let's define what is meant by a simple random variable, and I mean that literally. It's called a simple random variable. If you have a probability space consisting of a non-empty set omega, a sigma field curly F, and a probability measure P, a function x from omega to r is defined to be a simple random variable if 2 properties hold. So number 1, it needs to take on only a finite number of values. So it needs to be discrete, but also finite number, not countably infinite. So it can't take on, say, all integers or all positive integers. It's a finite number of values. And by the same token, they do not have to be integers. So maybe our random variable x takes on the value pi, e, and 7.2. That would be at least the beginning of the definition would be holding for this simple random variable. But we need number 2, and number 2 has to do with measurability without actually using that word. So we're going to say that for any x in the reals, if you look at the set of omega for which x of omega equals x, and this is my lowercase omega, it's almost a W, but it's not actually my W, it's more loopy. The set of omegas for which x of omega equals little x, this set needs to be in F. This is what it means for this simple function to be measurable with respect to F. This set is known as the inverse image of the real number lowercase x under the function capital X. And real quick, I'm just going to revisit an example. We're going to do nothing new but use the new notation. Oh, and by the way, this set will eventually, I'm not going to do it yet, I want us to get used to this first, but this set will be abbreviated as capital X equals little x in brackets. So if you see something like this in any measure theoretic probability book, they are referring to a set in omega. So it's really just shorthand for what is written here. So back to our 3 coin toss example, and I have a sigma field defined using that event A, where we see at least 2 heads, and A complement. Now I'm going to add on another sigma field. So before I called it curly F, but right now I'm going to call it curly F1. Suppose that x is a random variable that takes on the value 1 if we see at least 2 heads on the coin flip or 0 otherwise. We know how to define probabilities for x in terms of the probabilities we know for A and A complement. So again, the only reason for this slide is just to write it with this slightly more formal notation. If we look at the set of omega for which x of omega equals 1, that is precisely the set A. And A is in F, and therefore is measurable. So I actually don't even need to bring probability into it. That's automatically there for the sets in F. We just want to show that these inverse images sets are in F. Similarly, if we look at the omega for which x of omega equals 0, that corresponds to the set A complement, which is in F. And what if we want the set of omega for which x of omega equals 7.2? That's not happening. There are no values in the sample space that will give that value. So the inverse image of the value 7.2 under this function x is the empty set, and that is in F. If we instead let x be the number of heads in 3 flips, taking on the values 0, 1, 2, or 3, and we stick with the same sigma field, curly F1, consisting of the empty set, A complement, and omega, this x is not measurable with respect to F1. For example, if we look at the set of omega for which x of omega equals 3, getting 3 heads means we're looking at the outcome heads, heads, heads. This is a singleton set, and the probability measure has not been defined for that set for us at this point. So this x is not measurable with respect to the sigma field that we happen to be working with right now. If we let curly F2 be the power set for omega, this is the collection of sets consisting of all possible subsets of omega, and we have defined probabilities for all of those, then we will have enough information to find probabilities for this random variable being the number of heads in 3 tosses. So this random variable x defined here is measurable with respect to F2, but again, not measurable with respect to F1. And this sort of begs the question, is there a smallish sigma field for which this x is measurable? And that's coming up in the next video. An indicator function. Outside of measure theoretic probability, you could use these functions. So I'm going to let A be any set of real numbers. This has nothing to do with a sigma field at this point. I'm going to define a capital I sub A of x to take on the value 1 if the x you're plugging into this function is in A and 0 otherwise. Other common notations for this capital I is like a double-lined 1 like this, sometimes a chi, sometimes 2 square brackets known as an Iverson bracket. You can use your favorite notation, but I'm just going to use this sort of capital I. Okay, so we've been out of measure theory for way too long. Let's look at a probability space consisting of an omega, a curly F, and a P. I'm going to take any set A. This is not the previous A with the heads and tails. It's just a generic set A. And I'm going to define an indicator random variable which takes in values in omega, so x of little omega. I'm going to define that to be the indicator that takes on the value 1 if little omega is in the set A and 0 otherwise. I claim that this is a measurable function if and only if A is in the underlying sigma field F. Let's look at some values here. The set of omega for which x of omega equals 1 is A, and A being in F is what we need for this to be a measurable function. The set of omegas for which x of omega equals 0 is everything not in A, so A complement, and we need that to be in F for this to be a measurable function. And finally, the set of omegas for which x of omega equals 14.87 is the empty set, and we need that to be in the sigma field. It is in every sigma field. So we are guaranteed that this indicator random variable is measurable if and only if the set A comes from the sigma field F. Let's boost this indicator example up a little bit. Let's suppose we have sets A1, A2 out through AN, and suppose they form a finite partition of omega. So by partition, I mean these sets are disjoint, they are non-overlapping, and yet taken together, the union of A1 through AN fills in the entire omega. I'm going to define a random variable here, x of omega, to be the sum as I goes from 1 to n of a real number, A sub I, times the indicator on the set A sub I of omega. Then this is definitely a simple random variable. It takes on a finite number of discrete values, little a1 through little an, and as a rule, we're going to want to make sure those are distinct, but they don't have to be. But if like A1 is the same as A3, you can just define the two background sets, capital A1 and capital A3, into one set. and just have one term in there rather than the A1 term and the A3 term. That probably doesn't make sense. Well, I'll write that down later. So X is a simple random variable, and we have to have that measurability. So the inverse image, it's going to spit out either 0 if all the indicators are off, or little a1, little a2, up through little an. And the inverse image of, say, little ai is capital AI, and those are in F. So this is measurable with respect to F. There's a few more things to check, but it's measurable and has that finite number of discrete values. So this is a simple random variable. Actually, any simple random variable can be represented this way as a sum of indicators like this. So if it's simple, it has to take on a finite number of values, and you look at the inverse image of each of those values under the map X, and you find the omegas that map to, so maybe it takes on the values little a1, little a2, and little a3. Then you can find the omegas under which you get little a1, and the omegas that map to little a2, and so on. And those inverse image sets, those omegas are going to be the capital A1, the capital A2, and the capital A3. So any simple random variable could be written as a sum of indicators like this. So to reuse one of our previous examples, suppose we're flipping a coin 3 times, and suppose that the sigma field we're working with is the power set. So everything is measured. I'm going to let X be the number of heads in 3 tosses. So this takes on the value 0, 1, 2, or 3 if omega is tails, 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 or in this set, and so on. We can represent this right here as a sum of indicators. This is getting a little messy because these sets that I'm putting in the subscripts are quite long, but I can define X of omega to be 0 times the indicator that little omega is tails, 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 plus 1 times the indicator that little omega is in the set heads, tails, 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 heads, tails, or tails, tails, heads, and so on. So if you plug in a little omega here, if omega is, say, heads, heads, tails, then that is going to be in this set right here, not in the others. So all these indicators are going to be 0, except this one, it's going to be 1, and you're going to be left with only this value right here, which is 2. So X of heads, heads, tails is 2. Okay, so we have an underlying probability space, including a sigma field. We have a random variable X. Let's assume for now it is simple, and it is measurable with respect to F. If we take another sigma field curly G that's a subset of F, the random variable X could be measurable with respect to this curly G. And what that means is that inverse images of all real numbers under X have to be in curly G. We already know they have to be in curly F, and curly G is contained in curly F, so they're already in here, but they have to be in this smaller sigma field. If so, we say that X is measurable with respect to G. And again, we might write this set in a shorthand notation of just capital X equals X, but it is a set from omega. So suppose that we have the probability space, we have a random variable X that's measurable with respect to the sigma field F. We have a curly G, which is a sub-sigma field of curly F. And suppose that the random variable is measurable with respect to curly G. If you take any subset from the reals, I'm going to call it H, and this has nothing to do with sigma fields. It's not even in that space. It's in the reals, not in omega. Then if you look at the set of omegas for which X of omega is in H, which we would abbreviate like this, but it really means the set of omegas for which X of omega is in H, we can write this as the union over all X in H of the set of X's for which X equals little x. Then we're unioning over all little x in H. Is that in the sigma field? It's only closed under countable unions, and H might not be countable, but X is simple. So this union is equivalent to unioning over H and only picking up the finite number of values that X could take on. Right? The omegas for which X equals, well, let's do the actual example. One of our 1, 0 random variables. The omegas for which X of omega equals 14.7 is the empty set. And so we can drop those from the union. My point is we can write any union for any even uncountable subset of R as a finite union if we have a simple random variable. And that means that we have finite additivity, which is a special case of countable additivity. We have that any set that looks like this for any H subset of R is in the sigma field F. So it's measurable. One main example in today's video was this 3 coin flip where that other person gave us a probability measure for a particular set A, and we surmised the probability measure for A complement. And we looked at a random variable X being the number of heads in 3 coin flips, and we determined that that was not a random variable with respect to that space. We only know how to compute the probability measure for the set A consisting of all the outcomes where we have at least 2 heads and A complement. And we also talked about how X is measurable with respect to the power set, meaning all subsets of omega, meaning that if you have defined probabilities for all subsets of omega, then you're good to go with defining probabilities for this X. But, as I mentioned before, is there something in between? There is, maybe, and that would be the sigma field generated by X. So that's what we're going to talk about next time. If you come back, I hope to see you in the next one.